In this video, I'm going to work through the review problems I assigned from Chapter 3 on page 111. So that's going to be 11 through 16. In this section, the instructions say, it tells us that the function is not going to be differentiable at 0, and it wants to know what the reason is. And we know that we can take the derivative of any function except for where they're discontinuous, where there's a corner, a cusp, or a vertical tangent. If it's a corner, generally we think of those as two different linear parts coming together, so think absolute value. With a cusp, we think of two curved spots coming together. Generally, we think of the slopes heading towards infinity, one way or the other. A vertical tangent speaks for itself, as does discontinuity. So in this section, if you graph them and you look carefully at the graph, then it should answer the question for you. You also ought to be able to piece together kind of what they look like based on our knowledge of these functions. So on the test, I might let you use your calculator, but it's worth the practice to see if we can figure it out without them. So for me, I don't even have my calculator handy, so I'm going to rough sketch them, and some of these might be pretty rough. Here we have a piecewise function on number 11, which gives us the arctangent for all values except for 0. And if you know the graph of tangent, then the arctangent would just be the inverse and would look something like this. Except at 0, on arctangent the value would be 0. But here they're telling me I want at 0 the value to be 1. So let's just estimate that 1 would be right about here, and then that would make us having a hole at this spot. So then number 11, again, it's pretty obvious at this point that it would be because of a discontinuity. If you graph this on a graphing calculator, it'll help you get the individual pieces, so you really could graph the arctangent graph and see what it looks like, and then realize that we'd have to force the value to be up at 1, and then there'd be discontinuity. So the graphing calculator will assist you to some degree, but it can't do all the thinking for you. Okay, so now let's look at number 12, and a couple ways we could approach this. I think maybe the easiest is, again, you could just do it on your calculator and let it do most of the work for you, or we could get a little bit investigative here and realize that we could rewrite the math problem to be x to the 1/5 to the 4th power. And the 5th root of a function, you can plug in negatives and take the 5th root of a negative number. And so once again, having sort of a basic understanding of functions, the line y equals x would just be, this 45-degree line. Any power greater than 1, x to the 1st, would then start to curve up and look more like a parabola. Anything less than 1 starts to curve down and look more like square root. So we know that square root graphs in general look about like this, and so a 5th root graph is going to look about the same, except a 5th root graph we can do positives and negatives. So that'd be x to the 1/5. So then we're going to take those values and go to the 4th power, which would essentially, changing pen colors here, it's going to affect the values, the y values, but most specifically when we go to the 4th power, it's an even power, so negatives become positives. So we get is some version of the graph that would look something like this. So the red would be the total graph of this, and that indicates that we have a cusp. Alright, this next one, I'm not sure, exactly what previous learning we would want to, directly apply to this, but let's just kind of piece this thing together. we have the square root of x squared. So for the most part, that would pretty much seem to be x plus 2. So really this appears to be the graph of 2x plus 2. And so if we graph that, we get a y-intercept of 2 and a slope of 2, so it'd be a little steeper than that, but essentially we're linear. And theoretically, it would just continue and be linear the whole way. Except, let's go back and take a look at this. If I put in a positive value for x, and then I square it, it stays positive. And so the square root of a square gives us back to the beginning number. For example, if I put in a 3 and I square that, then I get 9. And I take the square root of 9, I get 3. But notice what happens when I do it with a negative number. A negative 3 squared becomes 9. The square root of 9 is still 3. But notice I didn't start with 3, I started with negative 3. So we, in fact, for the negative values, we don't get back x, right? We didn't get back the number we plugged in. We plugged in negative 3 and we got back a positive 3. So what we in fact got was the opposite of x. So when I plug in a negative number, I actually get a positive number. And so if I'm not mistaken, and again this is one I would definitely want to verify with a graph, I'm pretty sure that the values are going to get a little bit strange here. So let's just test it. Let's plug in negative 3 and see what happens for the full answer. Negative 3 squared is 9. The square root of 9 is 3. So then that gives me a negative 3 for x plus positive 3 plus 2, which is 2. So certainly not following this pattern right here, because at negative 3, this graph is showing, maybe a negative value. Let's try it with another number. Let's go negative 4. If I plug in negative 4, it turns into 16, which turns into 4. And this would be negative 4. And we're left with 2 again. So what seems to be happening is we actually are just getting the line y equals 2, which is not at all obvious from the graph. So, based on our evidence, it appears that we have a corner. Alright, I'm going to try and speed excuse me. 3 minus the cube root of x. The 3 minus is just going to shift it vertically. It's going to, number one, the negative will flip it upside down from whatever it looked like before, the parent function. And the 3 would move it up. So really, whatever issue we were having isn't going to be changed by these numbers. So we can answer this question simply by really analyzing, what's the cube root of x look like. And the cube root of x should look a lot like that fifth root of x graph we did earlier, which looks about like this. And since they tell us it fails, then that's kind of a hint that we really need to be careful on this. It's not a corner or a cusp, but what actually happens is we get a vertical tangent right there. And the vertical tangent ones are the ones you got to really look out for, because they appear like they work. I mean, there's nothing really unusual happening there. There's no V's, no cusps, no discontinuity. So a lot of people drop their guard. Alright, so absolute values affect positive numbers and negative numbers differently. So on 15, I think we need to attack it a lot like we did the problem above it on 13. So plugging in a positive number, the absolute value actually does nothing. So for positive values, we really just have the graph of 3x minus 2x minus 1, or the graph of x minus 1. Plugging in negative values, in fact, is going to have a difference. So let's kind of look at a graph that we're going to start so far. So we have a graph of negative 1 as a y-intercept and a slope of 1. So that's what I get for positives. Now let's plug in a negative 1 and see what happens. So I plug in negative 1 and I get negative 3. Negative 1 becomes positive 1. 1 minus 2 is negative 2 minus 1. So I get negative 3, 4, 5, negative 6. So here I was doing a slope of positive 1, moving up from a y-intercept of negative 1. And then when I plug in negative 1, the value is way down here at, what did I say, negative 6. So what happens when I plug in a really small number but negative close to 0? In other words, what's happening as I approach 0? Am I connecting to this point? Am I going somewhere else? Really what I'm asking is, what's the limit as x approaches 0 from the negative? So if I plug in a number that's almost 0, this goes to 0, this goes to 0, and I get negative 1. So it does appear that I am approaching, excuse that mark, approaching negative 1. And so I think I've got enough evidence. I think it's fairly anecdotal. I'm not rock solid on this. I might want to verify it with more values. But it looks like a excuse me, looks like a corner. And then we get to 16, which I've written wrong here. It's actually the absolute value of x. And so I think maybe the best way to approach this one would be to look at this as the absolute value of x raised to the 1/3 power. And so we know that the absolute value of x graph is a v, and then any number raised to the 1/3 power, makes it smaller. So that would mean when I'm out here at like the 0.88 would actually be the point. Plug in 8, absolute value of 8 is 8, 1/3 root of 8 is 2. So it drops it down. So what I think is going to happen is I'm actually going to get a graph that's going to turn more into a cusp. Alright, so that's the end of those problems, and I think I've done them all right. I probably would want to verify a few of them with a calculator, but I just wanted to demonstrate that some of these problems can be solved, and you can reason through a lot of these, even if a couple of them maybe were a little hard, like number 15. The practice of trying will make this a little bit easier for you. Okay, so I'm going to end this video now at 12 minutes, and we'll do another video for the next section.